My name is Ari Gesher. I'm a senior software engineer at a place called Palantir Technologies, and I'm here with Lauren Chaparro, who is a forward deployed engineer on the Helix team, which looks at sort of applications of our software in the health space. So I'm going to start with sort of talking a bit about the big data space in general and some of the limitations and what we're seeing in the technology today, then talk about how to build interface around this to actually deliver database decision making to actual users who know what the data is about. And then Lauren's going to take us through a pretty extensive demo of what one of these systems looks like. So I want to start sort of with a very brief history of big data. So here, as you may have read about, we see the size of data doubling over time. No, I'm just kidding. In all seriousness, the beginnings of big data are probably in 1992 when a company called Teradata built a 1 terabyte database for Walmart. But the modern era of big data sort of began right around the turn of the century, and I think it's awesome that we can use that phrase again, right around the turn of the century, with the creation of horizontally scalable technologies that can do large-scale data processing. And so if we sort of look through this timeline, you have things like Apache Lucene coming out right in the year 2000, GFS, the Google file system that Gmail runs on in 2002. Google releases their MapReduce paper in 2003. Hadoop, which is an open source implementation of the MapReduce algorithm in 2005. Google again releasing a paper in 2006, Bigtable. Hopefully I'm telling you things that you guys know, but Amazon's Dynamo system in 2007, and NoSQL sort of comes into vogue, the whole notion of NoSQL in 2009. Facebook came out with Cassandra, which is an open source implementation of Dynamo in 2008. There's sort of a theme here. And Google actually just came out with something a couple of years ago called Dremel, which is a system for interactive analysis, and that's really the thing that I want to dive deep on. But first, I want to show you a movie trailer. So this is a trailer for a movie called Truth in 24. It's actually free on iTunes. It's really awesome. It's 90 minutes. It's shot by NFL Films. It's narrated by Jason Statham. It's fantastic, right? It's about the Le Mans team from Audi in 2008 trying to beat a much faster Peugeot team. And for those who don't know a lot about auto racing, and I didn't before I watched this movie, they say you can win the Indianapolis 500, but you just survive Le Mans, right? So Le Mans is a 24-hour endurance race where you just run the cars literally for 24 hours straight. It's sort of the pinnacle of high-performance auto racing. And so what you see at the heart of these race cars are these incredible pieces of technology. This is the Audi R10 12-cylinder turbo diesel injected engine, right? So why am I showing this to you, right? Well, it's kind of similar to Hadoop, right? It's this high-performance piece of technology, and when you download Hadoop, it's basically like being delivered a racing car engine on a pallet. And you're like, well, I want to go somewhere. And they're like, well, here's your engine. Have fun. And so to sort of even put to take a wider view of this, this is the Audi racing team from that year. So the guys in the gray and the red, those are the three sets of drivers for each car. The folks in the white shirts with the black pants, that's the crew. And that includes like mechanics, people whose job it is to just warm up tires before they get on the car, right? There's a meteorologist on staff. They probably have someone running radios. There's an incredible amount of infrastructure that goes around running this engine. And the same is true of big data, right? So if you look at the places that have seen incredible success with these technologies, the places that are even creating them, places like Google and Facebook, they have incredible operational staffs and do some of the best systems engineering in the world. When we look at the healthcare space, the users, the race car drivers, look something like this, right? So doctors, scientists, researchers, maybe Dr. House actually doesn't count. He maybe could do all this himself. But if you deliver them, a piece of software like Hadoop on a pallet, they don't know what to do with it. They need something that's more like this, right? That has the interface that they need to be able to drive this to do the decision, the data-backed decision making. And so today, to do something trivial in Hadoop requires being able to write code. And the people who know the most about health data and health outcomes and making these decisions, right, they're not going to follow this like multi-page tutorial about how to write a trivial Hadoop job, let alone, implement some large-scale processing thing. So these technologies are great, and they're sort of raw capability. And in general, there's some movement of interface. So what you see here is just a snippet from a blog post on Astrodata. They build these really great scalable column stores that can hold lots of data and retrieve it very quickly. They were very proud in this blog post, and rightfully so. They managed to bolt SQL onto Hadoop, right? So like they've sort of taken it one step forward, but again, you know, the average doctor isn't, or you know, public health researcher isn't going to know SQL very well and isn't going to be able to sort of build the very complicated queries that you need to sort of deal with the massive data and make decisions based on that. So at Palantir, what we do is we build these data analysis systems to be used by sort of mere mortals, as it were, right? And so the internals of the system look kind of like you'd expect any other big data system to look. You know, we've got kind of a massive server cluster with different pieces that have all been put together. We've made a lot of the systems engineering decisions for the customer, where you can kind of just one-click deploy it. You set up some machines, you put the software on it, you hit a button, and it all gets sort of set up, and you ingest your data. But the important piece is that we've made it with an incredible amount of user interface, right? So like our engineering teams on the one hand are worried about all the data plumbing, but on the other hand are looking really deep at how you actually made up this incredible processing infrastructure with things that regular people can use to bring the data to the subject matter experts. And when we think about this, we think about three different things. So what you're seeing here is a little bit of a preview of the demo. It's actually a completely different data set than we're going to be looking at. So what we're building are actually abstract tools that can be customized to specific workflows. Once you put you can think of them as empty vessels, just like a database, right? You put in your data, you put in your data model, data from many different sources, and it maps into user interface that lets people move through this data. So the video here is actually looking at disease early warning based on information compiled from folks with cell phones going out and talking to farmers in rural Uganda. But the thing that I really want to focus on are the three pieces that are important here, right? So the three sort of aspects of these interfaces that are really important. One is that they be familiar. And by familiar, I mean that when you sit down as a subject matter expert, your language, your vocabulary needs to be a first-class citizen in the interface, as opposed to having to do this sort of indirect understanding through things like tables and rows and columns and key value store buckets, right? Like no one really thinks about problems in the real world in this way. They think about it in terms of the things out in the real world that they care about, and they look at the data as a proxy for those real world processes. So familiarity is the first point. The second point is that it needs to be interactive. And so not only are most of our subject matter experts not writing the code that's going to run Hadoop, there's some built-in latency where they're maybe talking to a data science team who then have to spend a day writing the job, and then they run the job, which takes 12 hours, and they get back an answer, and they're like, okay, it's 42, and then, okay, wait, but we forgot about, bringing in the board certification, so how does that change the model? And then they wait another 2 days until that happens. And so it really breaks up the train of thought, and a lot of the things that we're looking for in analyzing health data are actually very complex and subtle, and they require a lot of injection of human insight at every step along the way. And when you're thinking, the frame rate on your thinking is something like 2 days, it's really hard to come up with a nice, long, deep, complex analysis. And so the last piece is actually expressiveness, right? And so being expressive is a proxy for how compactly you can represent the instructions that you're giving to these incredible computing devices that we've built, right? So I can say, show me all of the reports of people asking about, a disease that's afflicting chickens in this district in Uganda during this time. It's actually a pretty easy query for me to formulate in my head, but if you give me this data in a SQL database and ask me to write the queries to do it, that system is not incredibly expressive. It's powerful in that you can write any query that you could possibly imagine, but the time it takes me to express that to the computer is actually quite long, where I should be able to, in a couple clicks, actually drill down into that data and then ask the next question, right? Which is, which direction is this coming into the district from? Where are we seeing it from other districts? So I want to be able to very compactly represent the work that I want the computer to do. And so that's sort of the high-level philosophical overview. And what Lauren's going to show you today comes out of some work that we're doing with an organization out in Washington, D.C. called the Center for Public Integrity. And so they're an interesting organization. They're sort of broadly interested in transparency and accountability in government and public institutions. And we've done a bunch of other work with them in the past. So the first workflow that we did with them actually looked at 350 million mortgages over 10 years in the United States. We used it to test drive a piece of technology that we built called Horizon that does this sort of like large-scale filtering in under 10 seconds of every query that you ask. And we were very quickly, literally within about 30 minutes of getting the data up and playing around with it, start finding hotspots of subprime mortgage lenders doing predatory lending against specific demographics and neighborhoods, like writing loans that were incredibly just way too expensive for what was going on and say, hey, look, these people at this branch, at this bank are causing problems. And this was something that no one had really seen before. On a more somber note, for those who don't know about Daniel Pearl, he was a journalist that was covering the war in Afghanistan. He was abducted in Pakistan and murdered. And someone was arrested by the Pakistani government and sort of tried and convicted for his murder. But it was sort of broadly believed that this was not the person who was actually responsible for it. There was actually a much larger group of people, and this guy was actually a patsy. And so the Daniel Pearl Project at Georgetown worked with CPI to pull in all the available data about what happened to Daniel Pearl, and they put together a report called the Daniel Pearl Project that you can go find online. And they used Palantir to pull all that in. And most recently, we worked with, through CPI, with a group called the International Consortium of Investigative Journalists on a very long story that they were doing, cracking open illicit human tissue trafficking networks in Eastern Europe, which are basically stealing body parts off of cadavers to turn them into implantable medical devices in the United States. And this is, again, something the internet knows all about it. But today, what we're actually looking at is Medicare claims data. And so CPI got access to a large amount of claims from CMS. It's 400 million claims, 1 billion medical procedures, about 30 million beneficiaries, and 700,000 physicians. And specifically, the workflows that we're looking with them are looking for different types of upcoding fraud, where physicians are sort of overcharging for services from CMS. But we've been playing around with this and saying, well, what else can you do when you have this data? And so what we've done is actually build an instance that has a bunch of additional data sources integrated into it, into the Palantir platform. So there's the National Plan Provider Enumeration System, which gives standard IDs across all payers and providers. There's the Dartmouth Atlas project, which has hospital-specific performance data related to end-of-life care. PubMed, which we all know and love, hopefully 22 million biomedical journal articles in one place from a number of different sources. And then we also brought in the list of excluded individuals and entities that have sort of been caught doing fraudulent behavior in the past that's maintained by the Department of Health and Human Services Office of the Inspector General. And finally, some US Census data. So what we're going to show you today, unfortunately, is not the real data because we can't show that to you. That data is actually very closely kept and it's considered to be very sensitive. But we know a lot about that data, and we've sort of distilled it down to a notionalized set of synthesized data that kind of looks like the real data but has no actual real people's information in it. And it's running on sort of a tamped down stack on a single laptop. Normally that sort of big server architecture I show you will be holding these sort of millions and millions of records. But Lauren's going to walk you through a bunch of different workflows looking at this data, and you can sort of see what's possible once you can deliver the data to the decision maker. So, Lauren?
Great. Thank you, Ari. I know you guys have been waiting to see what is living inside this computer. So to get started, I'm going to be using hospice care as a lens. So let me quickly switch this over. Did it work? Awesome. Okay. So for those of you who aren't familiar with hospice care, it's typically a treatment option for patients who have about 6 months left in their life, and it focuses on a patient's total well-being. So entering hospice care marks an end to harsh treatments and a focus on gentler palliative care. They say it's the best medical care that nobody wants in the U.S. And unfortunately, it's also been in the headlines recently with a lot of fraud and abuse from CMS, with for-profit hospitals being fined and penalized for continuous billing for these patients. So today I want to show you how we could use Palantir to both review high-level policy issues as well as dive into understanding this kind of fraud. So just to explain what you're looking at over here, this is my homepage. So as Ari mentioned, I think this couldn't possibly be more familiar to everyone. Looks very similar to my Google search bar. And also you can see all of the data that Ari mentioned that we've integrated into our system. So to get started, one of the classic policy considerations I might want to think about are supply and demand. So are there parts of the country that are better or underprepared for escalating demographic shifts? So to take a look at that, I've actually loaded in census data, and we're looking at my map, and I've colored this based on the population growth in people aged 65 or older. And I can contrast this to a supply metric, so thinking about density of hospice facilities in the U.S. by county. And here I've actually preloaded that in. I'm going to make it a different color. And we can see these two metrics as they're overlaid on the map. But this really isn't telling me very much. Like it's a really lovely picture, but ultimately I want to see if I can identify outliers for where places might be under-resourced. So here I brought in a correlation, and it's looking at U.S. counties, and I've already added my population, my density metric, and now I'm just going to quickly add my demand metric, so that's my population growth. And with a couple of clicks, we're able to generate a quadrant to say, over here on the far right, we have high growth counties, and then on the upper quadrant, they also have low density as far as facilities. So again, with a couple of clicks, I'm able to generate a couple of high priority targets to consider for capacity and resource planning.
I'm sorry, what did it mean to be on the top right?
That you are potentially under-resourced. So
Under-resourced and growing too fast.
Growing too fast without enough facilities.
You have a lot of people that need hospice care without a lot of hospices.
Yeah.
So what we sort of seen so far, I mean, hopefully it speaks a bit to the piece about familiarity. This is like the kind of information that's going to be delivered to you in a big database or a spreadsheet. But as soon as you can actually view it on a map, drop it on a graph, and sort of very quickly see what's going on, the things that you're looking for actually jump out at you. And you'll note that the ontology that we use to build the data integration that underlies this, it surfaces in the interface. We'll sort of see that a little bit more in depth as we dive down it and take a higher resolution picture of the data.
So I just went through a policy overview, but I'm also interested in understanding fraud. And like I mentioned at the very beginning, we've seen that fraud has been occurring by physicians certifying that a patient is terminally ill, and then 6 months later recertifying that this patient is ill. So the process continues, and this service that's supposed to be reserved for people at the end of their life gets prolonged. So I also know that once someone who's been acting fraudulently has been outed in the media, they're probably going to change their tactics. So I need a tool that allows me to explore my data to generate new hypotheses and identify them within the data set. So to do that, I'm going to start by looking at high-level trends again. And in this case, I'm going to focus on some survey data from the National Hospice and Palliative Care Organization. So down here, I'm going to take a look at utilization metrics that might give me some information about where certain areas might be outliers. So one of the things I might look at is the percentage of facilities offered in these states that offer inpatient care. And inpatient care is when a hospice patient is actually spending time in the hospital. I can quickly see that Florida is an outlier here, which we might expect. This is also a retirement center. I can also look at volume, so total days on hospice care, and again, we're seeing Florida as an outlier, possibly makes sense. But let's look at accreditation, so what percentage of the facilities in this area have received any form of accreditation, and Florida is relatively low. So needless to say, I'm interested in Florida. This seems like a place where, given the high volume of patients, given these kind of outliers, there might be some fraud happening here. So at this point, I'll want to bring in my claims data. So I've actually created a search to bring in hospice claims from Florida. Being able to explore my data requires being able to understand both high-level trends as well as fine-grained as a specific physician or a specific claim. So now I've brought in my claims from Florida, and I'm going to use these as a data set to explore. So I'm going to select all of these, drag them to my Object Explorer. And Object Explorer is my tool to be able to look top-down on all of the data that I have integrated into this system. So as you can see, I pulled in about 1,300 claims from Florida, and I'm interested in understanding some physician-specific metrics. So I'm going to group by my NPI code and look at how many average utilization in a hospital. So again, I typically expect about 1 to 2 months of time for a patient to be spent in a hospital when they're on hospice care. But what I can see here is that on average, some of these physicians, so each row here represents a physician, has an average of almost 6 months, which is very shocking. And then this sum here represents the total number of patient days that were spent in a hospital. So this could perhaps mean that they have a high volume of patients, that their patients are the sickest and they just need the most care. But again, looking over here, with a maximum of a patient staying in inpatient facilities for hospice for an entire year, this is looking interesting. So I might want to dig down on this physician specifically and try to understand what's happening. So what I've just done is moved my data from that Object Explorer to my virtual whiteboard, which I call the graph in Palantir. And as we can see, these all represent individual claims. And I'm going to do a quick search around to be able to bring who the physician is who's been servicing these claims. And the way we're able to do that is through the integration of both the claims data with the national registries. So now I have a physician, and it's not a real person, but Dr. Janice Cooper, who I'm interested in comparing. We've said over and over, Florida is different. So I want to be able to compare Dr. Janice Cooper specifically to what I might expect in Florida. So to do that, I'm going to take her to my dashboard and actually have a separate dashboard where I can get a snapshot, and this has been customized for the metrics that I care about as an analyst. I can see just a distribution of her claims. I can see that number again, the number of days her patients typically spend in the hospital on hospice is very high at almost 6 months. And I go and see that her cost per claim is about $14,000. I don't really know if that's high or low at this point. So I'm going to rapidly generate a benchmark on the fly by only looking at the hospice claims in my database and only looking at those hospice claims that are set in Florida. You can imagine doing this today. That might require running a very complicated SQL query or asking someone else who knows how to write that query to do it for you. And so what I have as a result is a side-by-side comparison, something that feels more like apples to apples. And you'll see here my second group, my benchmark is in orange, and my original physician is in blue. So looking down, I can see that this number maintains its strength as an outlier, that typically in Florida, patients are spending more like 3 months in hospice, and that the average cost per claim is more like $7,000, $8,000. So I have a red flag. Clearly, none of this is specifically indicative of fraud, but I'm getting a lot of signals. So I want to go back to my graph now to understand everything I know about this physician and these claims, and using all of my data. So I'm going to quickly select everything and do a quick search around. Actually select everything and do a quick search around on the facilities so that I can understand the geospatial distribution. And what I just did is I brought the facilities that are associated with these entities, and I can clearly see that there's a hospital associated with my Dr. Cooper, but that there's these 2 other hospitals associated with all of these claims, and that there doesn't exist a link between Dr. Cooper and these hospitals, which I would expect that any claim that's generated at this facility would also be tied to a physician who works at this facility. So by doing a quick search around of all of my data, I can see that something is looking very out of whack. It could definitely be identity fraud, where a physician's specific number has been hijacked and now they're submitting expensive fraudulent claims on their behalf. And just to bring home this point, I can take a look at these on my map and see where they are. So I'm going to get rid of all those claims that I brought here originally and now just zoom in on Florida. And so these are the hospitals that I had on my graph, and I've just dragged over to the map, and there's clearly some geographic dispersion here. And this would be very hard to see on a spreadsheet. And it's been much easier. It's just almost too obvious that something is going on here looking at the map and this data. So in summary, with Palantir, I was able to very quickly generate some targeted policy recommendations for areas of potentially under-resourced for hospice, and identify a new tactic of fraud. So my investigators can now go out and try to seek out specifically who's been submitting these claims effectively using my resources.
So it's this ability to sort of seamlessly pivot between different data sources to sort of put together a full picture, and you see the entire story emerge. And for someone who actually understands the data and what it represents, it's really easy for them to ask a question like, so where is this hospital? Is this fraudulent? And very specifically with a workflow like this, maybe for folks who are a little more technical in the audience, building automation to discover this kind of thing is incredibly difficult. And it's the kind of thing where if you put it in the hands of an experienced analyst who understand how these things go and let them dig through the data, they can find these things very, very quickly. But to build some sort of data mining tool that can recognize this as fraud across these multiple data sets, given sort of changing tradecraft, is incredibly difficult.
So I just walked through an overview of how I might go top down and drill down into a specific physician or claim, but we could also see Palantir at a patient's bedside, helping to use data to inform a physician, both in their treatment and also in their referrals for placements of places of care. So I'm going to switch gears, and we're going to focus on diabetes. And I'm sure it goes without saying, you're all aware diabetes is considered a national epidemic with over 79 million adults at risk of developing the disease in the next 10 years. And there's a high degree of variability, so this is certainly not a disease where it's one size fits all for each patient. So today I'm going to be playing the role of a case manager who's reviewing my patient and considering some options. So just get started. I've preloaded my patient onto my graph, and I can quickly review all of their previous medical encounters to get an update on what they've been going through recently. And I've sorted them based on their timeline. So quickly, I can see that he has asthma, he's got high cholesterol, high blood pressure, he came in for a hernia, he's had bronchitis. I'm just quickly going through my procedure codes over here to get a quick snapshot about what he's been going through, and also see that he has the diabetes diagnosis. Additionally, especially in healthcare, I'm going to have other information, so I know he's morbidly obese, and I also know that we've been trying to conservative treatments such as changing behavior, changing diet, changing exercise, and that these haven't been successful. So a natural consideration is bariatric surgery, which is kind of controversial and has a lot of risks associated with it. So there's two types of bariatric surgery I might consider: laparoscopic banding and gastric bypass, laparoscopic banding being a lot less invasive of the two. But I want to learn more. And so perhaps you've noticed this little one up here in the corner, but I've asked my teammates if they have any good input on this, and one of my teammates has sent me an article. So I can quickly access this and add it to my graph to review. And I see it's from PubMed. So he might have, we were able to search PubMed within Palantir. I'm not going to show that today, but he may have searched for it and found it and sent it over my way. So I'm going to explore this. It's from the American Journal of Medicine, and what I've seen is he's actually tagged diabetes to the document, so if I were to search for diabetes, this would come up. But in reading it, I can see that there's definitely different benefits and risks associated with these two surgeries, but one thing that strikes me is that diabetes is resolved in a greater degree in patients with the gastric bypass other than as opposed to the laparoscopic banding. Ultimately, my decision is coming down to a holistic consider of the patient. But to keep in mind that I use this as a part of my decision making, I can quickly create a link between my patient and this document, such that in the future I can reference back and know exactly what I was thinking about when I made this recommendation. So the patient and I have a conversation, take into their preferences, the risks and his specific comorbidities and other factors, and we decide to go with the gastric bypass surgery. Now, ideally, we'd want to be able to use data to inform what hospital he should be undergoing this very, very significant surgery. So one of the things I know is that my patient doesn't want to travel very far. He's not able to move very far. So I'm going to create a data set based on the location he's currently receiving care. So this is his medical center currently. And what I'll want to do is merge both my claims data with other hospital metrics, such as the Dartmouth Atlas project, which provides outcome measures for hospitals. And there's additional sources we can imagine integrating here to be able to layer in to inform a decision about where to refer this patient. So, like I said, I'm going to take this to the map, and I see he's located in Houston. And I'm going to generate a sample set of hospitals that are in a reasonable distance that he might be able to travel to. So I'm quickly going to create a radius search around Houston. And I'm bringing in all the facilities in this area. So now it's hard to see here, but we've brought in a bunch of yellow dots, and these are all of the facilities within a driving radius of his current location for care. And I'm going to use these now as my data set to explore who's had the most experience doing gastric bypass surgery in Medicare patients like mine. So again, I'm going to create a data set. And what I'm doing now is I'm going to actually bring in the claims associated with these hospitals in order to explore what their current experience level has been with gastric bypass. And for the purposes of this demo, I've actually only brought in the gastric bypass CPT codes, but you can imagine for our entire data set, we'd have a lot more information here.
So Object Explorer that Lauren's using right now is sort of an interesting piece of user interface where it's based on this Horizon technology that I mentioned earlier, which was built to be able to query billions of objects in interactive time. And what you're seeing here is actually computation taking place on the server. So this is sort of a user interface proxy to calculations taking place on the server. What comes back are these views that sort of give you the results and let you pick the next step to go through and filtering through these sort of billions of records. We're using a few less in this demo, but when you a cluster that's scaled out properly gives the same kind of interactive time even across data at scale.
Great. So what I've pulled up are each of these numbers over here represents a hospital, and I can see the number of times they've conducted this procedure. And so now I want to explore these more because I know it's not about a single variable to choose a hospital. So I'm going to bring these facilities back to my graph. So now I have a hospital set for consideration. And like I said, I've added in additional data sources to understand how these hospitals compare on a couple of different quality outcome metrics. So I'm going to drag them to my heat map helper, where I can fine-tune across multiple variables. So especially for an invasive surgical procedure, I might care about the number of ICU days, the success rate of their surgeries, and quickly I'm able to drill down and generate 2 hospitals potentially for my patient to have this undergo this surgery. And so ultimately with Palantir, I was able to inform my decision making about a treatment through collaboration with my partners. I was able to capture my decision making and use multiple data sets in order to inform a referral for an invasive surgery.
So this is the power of user interface on top of big data, right? As soon as you can actually bring the data to the people who know it best and can sort of seamlessly pivot between not only different data sets, but different ways of looking at different data sets, decision-making becomes very fast and it becomes very rigorous. And so to sort of end the talk on kind of a philosophical note, I want to actually go back to 1997 when Deep Blue beats Garry Kasparov, right, in a chess match. So before 1997, it was a really cool sport to like build bigger and better computers to try to beat humans at chess. One day the computer wins. We need a new sport. So the sport that came out of the defeat of Kasparov was something called freestyle chess. And the way that freestyle chess works is it's a chess tournament just like any other, only there are no rules about how you come up with the moves, right? So you can read the tea leaves, you can roll the dice, you can enter Deep Blue, you can, most importantly, enter a team that's a hybrid of humans and computers working together. And so a set of these tournaments were sort of spawned, and as often is the case, someone builds a new chess-playing computer and they say, well, we should have a tournament to see how good it is. So in 2005, there was a tournament held in Dubai by a maker of a computer named Hydra. And Hydra was similar to Deep Blue, but much, much more powerful. It was a bunch of networked FPGAs that could sort of brute force the chess space very, very quickly. Also in the tournament were a bunch of grandmasters using laptops, sort of commodity hardware with chess software on them that could let them sort of move through big databases of moves and give them statistical analysis. And there were a bunch of amateurs, mostly who were probably in there to say, wow, I got my ass kicked by a supercomputer and a bunch of chess grandmasters. But the result of the tournament was actually kind of surprising. Hydra lost early on to a grandmaster using a laptop, which wasn't super surprising to a lot of people. If you can take human expert intuition and aid it with a computer, you can probably beat the brute force approach anytime. The thing that was surprising was the winner of the tournament was actually a team of amateurs based in the United States. You play these tournaments by mail, so they weren't in Abu Dhabi or Dubai. They had taken 4 different chess programs running on 3 different computers and built a little bit of custom code to chain them together. And they were amateurs. They weren't ranked in the chess world. They weren't considered chess experts, but they knew enough about the game to play, and more importantly, they knew how chess software worked. And so they built themselves custom interface that let them leverage the computers as much as possible. And in doing so, they were able to beat a grandmaster using basically equivalent computing power in the tournament. And so Kasparov actually wrote this whole piece in the New York Review of Books about this tournament. And the sort of the money quote from it was, weak human plus machine plus better process was superior to a strong computer alone, and more remarkably, superior to a strong human machine plus inferior process. And so here, when he's talking about process, he's talking about interface. He's talking about the boundary between human and computer. And so when we build these incredibly powerful interfaces that are familiar, and expressive and interactive, what we're doing is we're very, very efficiently getting the computers to do as much work as possible for us. And so we're sort of taking that race car engine that we were looking at earlier and building it into a car that has an interface that lets us, go wherever we want to go, find the answers that we'd like to find. This is what we do. We think there's a big future in this for big data. We know that the interface is the really big missing piece, and we spend a lot of time thinking about it, and we hope that you guys will too. So thanks for coming. And I know that there are drinks somewhere in 10 minutes, but we're happy to hang out and answer whatever questions you have. I know the AV guy said that there's a set of mics to ask questions. If you raise your hand, maybe it'll come to you. If not, I'll just repeat the question. So
how much effort is it going to preparing a set of data sources to be used through this interface versus just having people write programs to generate this query that does?
Sure. That's a really good question. So basically the question is, what is the cost of data integration? What does it take to actually get data into the system? So we've thought a lot about the problem of data integration. Fully half of our engineering team spends its time dealing with data integration, how you put it together to do this kind of querying. And we think that we've hit on some approaches that make data integration easier. We wouldn't call it easy because I don't think no matter what, it's not easy. There's no magic bullet in data integration. But the thing that we've done is increase the ROI for the work that goes into it, right? So there's two basic problems in data integration. One is that it has quadratic complexity. Every data source you add in, you run this n squared problem, right? Or every data source you add in has to be coordinated with all the other data sources. And so each time you add one, the cost of adding a new one goes up. So the way that we approach that is by building what's called an ontology, which is similar to sort of a schema in a database. And unlike sort of the academic approaches to ontologies like Core, Double, and OWL that you might be familiar with, it's not an attempt to encode the entire world. Instead, we try to keep it as constrained as possible. We only encode the things that you care about and nothing else. And once you have, and the important thing about the ontology is that it's composed in terms of human concepts, right? So rather than being about tables, rows, and fields, it's about Medicare claims and patients and hospitals, right? It's all the sort of nouns and verbs that the people who know the most about the data use to think about it. And so the ontology acts as a router. So when you do data integration on our platform, what you do is you integrate a given data source to your ontology. You don't actually care about any of the other data sources. And so each one of them has a non-trivial but fixed cost. And you know that by integrating a single data source with the ontology, you get all the other data sources for free. And so it acts as sort of like a hub or a router. And so what we see is that in general, our benchmark for sort of data integration is about 8 weeks. So from the word go, our software it deploys inside people's networks, right? So rather than it being hosted somewhere, you buy the software, you set up the computers, you run it on there, and our engineers come on site and sort of help with the data integration. And it takes about 8 weeks to get data up in a usable form. It depends on the scale of the data and the number of data sources. It'll vary there, but that's our basic benchmark. And once you've integrated a single data source, you kind of never have to touch it again. And that's the important thing is making it clear where the investment of time, energy, money go, what you get for that, right? And turning it into a fixed cost instead of this sort of unbound thing as the size goes up. Yes?
Bit of a geeky question. I heard you say that you're using Hadoop, right? How are you dealing with the lag in there? Because if you're doing MapReduce with the kind of queries you were doing, it would take 20 minutes to respond, right?
Right. So the interactive system that you're seeing here isn't using Hadoop. We use Hadoop in 2 different places. So we use Hadoop at ingest time. You can think about us doing this sort of massive transform of the data into a form that allows this sort of very fast interactive querying, and Hadoop is really useful for that. Additionally, when we've dealt with sort of machine-generated data sets, when we're doing things like cybersecurity or looking at web logs, we have really, really massive scale of data, and most of it you don't care about, but you care about having it all available, especially in things like fraud workflows. We use MapReduce to do sort of scoring of clusters that are then queued up for human analysis. So those are run as a batch job. No, I agree. The batch nature of sort of the MapReduce paradigm is problematic when building interactive systems. So we try to stay away from it as much as possible. Horizon, which we were looking at in Object Explorer, is similar to MapReduce, but it kind of doesn't have any intermediate steps. So basically, it lets you go through and touch billions of objects and build some sort of aggregate sum or calculation of it, but you do one pass, and then you get an answer. And there, it's just a question of really, really optimizing the memory store in such a way. It's all written in Java, but it doesn't use any objects, so you're all you do is run through your RAM as fast as possible. If you need to, you can actually distribute it out into sort of multiple sharded clouds to sort of run those calculations in parallel.
Sorry, one quick follow-on. Can people write on top of Horizon, or is it just
Yeah, you can. So each one of those views that you saw, the entire stack is actually customizable, sort of top to bottom. And so one of the things that we do when we do deployments is you say, well, here's the base level set of functionality, and then what customizations are needed, and we have sort of well-published APIs to do that. I was told that was the last question, or we have one more question is the last question. Yeah.
All right. So you used the word rigorous in describing this, and when I think of rigor in terms of big data and decision making, I think of statistics, p-values, confidence intervals, and I didn't see anything that looked like that here. Is that also a part of Palantir?
We actually do have a second platform that works very differently that actually does sort of statistical analysis and quantitative analysis. Rigor, though, comes in many different forms. It's a question of what your problem is. When you're doing a fraud workflow, rigor is actually just going down to the nth degree to see, are there problems here, right? And there you're doing sort of discrete analysis. And what you're looking at here, this is mostly about discrete analysis. The map and data fusion workflows that we're looking at the high level are about sort of integrating this sort of high level quantifiable statistics before you drill down to do the sort of the low level high resolution work as well. And so there's definitely a place for that sort of rigor, but I think it actually depends on what the problem is that you're trying to solve. Both of them are important, but completely disparate in a lot of ways. Thanks for coming. We'll hang out here if you guys want to come up and ask other questions.